Assalamualaikum and a very good day to everyone. My name is Nur Sarah binti Abdul Kali, and today I will represent my team in presenting our study titled Comparative Study of Numerical Methods in Solving Higher Order Ordinary Differential Equation. Before I begin, let me introduce my team members and co-authors. Alongside myself, we have Nurdiana binti Abdul Jabri, Anisun Nafisah binti Azmi, and our final author, who is also the corresponding author, Nurul Ainina binti Ridwan. We are from University Technology Mara, Terengganu Branch, Kuala Terengganu Campus. To start, let me briefly explain what ordinary differential equations or ODEs are. ODE is a mathematical way to describe how something changes with time or with another variable. For example, in mechanics, ODEs can be used to describe the motions of the pendulum. In electronics, they can model the relationship between current and voltage in a circuit. In chemistry, ODEs can help represent change in the concentrations of the substance during a reaction, and in biology, they are often applied to model population growth or the spread of the disease. So, ODEs are very important because they appear in almost every field of science and engineering. In our study, we focus on higher order ODEs. Higher order ODEs are equations with order higher than 2, such as third, fourth, or fifth order. They are important because they can represent complex systems more accurately. However, solving them by hand is often very difficult, and this is where numerical methods become very useful. Our study have three main objectives. The first one is to compare three numerical methods, which are Euler methods, EM, Adam Mountain's methods, AM, and Rajkata-Verbers, RKFO5 individually and combinations with the Richardson extrapolation, RE. Second, to evaluate their performance based on the currency and CPU times. And the last one is to determine the most suitable method for solving complex higher order ordinary ODEs efficiently. From the literature, a homogeneous differential equation is an equation where the function and its derivative were written on the left-hand side and the whole thing equals to 0. To solve this, it depends on the root of the characteristic equation. They can be discrete, repeated, or complex, which give different solutions. In terms of numerical methods, first, we have the Euler method, EM. This is the simplest method as it only uses the slope at the current point to predict the next value. It is very fast and easy to implement. However, based on the literature such as David et al. 2018 and Saleh 2024, Euler's method is generally less accurate when applied to the higher order differential equation. The second method is Adam Mountain method or AM. This is a multi-step method, which means it uses not only the current points but also the previous point to improve the next estimation. According to the study by Marlarvisin et al. 2018 and Saviviava et al. 2014, this method is more stable and provide more accurate compared to the Euler method. The third method is Rajkata method, RK. This method is widely known because it calculates separate slope within a single step before averaging them to get the more reliable approximation. In particular, RK4 and RK45 are the most commonly used versions as highlighted by Linfield and Penny 2018 and as well as the Benu et al. 2021. Finally, we included Richardson extrapolation or RE. These techniques combines results from the different step size to reduce numerical error. Previous research, such as Wahab 2017 and Bailey et al. 2024, shows that Richardson extrapolations can significantly improve the accuracy of Euler, the mountains, and also the Rajkata methods when solving higher order differential equation. On this slide, the formula of the numerical method used in our study are presented. We focus on three main methods, Euler methods, Adam Mountains, and Rajkata-Verbers. To enhance the accuracy, each of these methods was also combined with Richardson extrapolation. All methods were implemented using Maple software and tested on selected fourth-order ODEs problem. The approximate solution were then compared with the exact solutions in terms of the accuracy measured using relative error and the efficiency measured using CP times. Now, let's move on to the results and discussion. For the first problem, we implement all the methods, Euler and the mountains and RKF05, both with and without adjacent extrapolation in Maple software. The approximate solutions were recorded in the table. To measure the accuracy of each method, we calculate the relative error using the error formula. The results were tabulated and then visualized into the graph for clear comparison. From the graph, we can see that the Euler method is the least accurate. Its error curve moves further away from the x-axis, indicate larger deviations from the exact solution. Meanwhile, the Adam Mountains method shows better accuracy compared to the Euler, but still there are deviations slightly. When the Richardson extrapolations was applied for both Euler and Adam Mountains, it improved slightly their curve, moving closer to the x-axis. On the other hand, the RKF of 5 already give the results that are very close to the exact solutions. Adding Richardson extrapolation to the RKF05 showed no significant improvement, confirming that RKF05 alone already control the error efficiently. A similar pattern can be observed in problem 2 and problem 3. Euler remained the least accurate, and the mountains improved with Richardson extrapolations, and RQF45 consistently produced the best accuracy even without Richardson extrapolation. In terms of the CPU times, the Euler method was the fastest, followed by other mountains. RKF45 require more times due to its complexities. With Richardson extrapolations, CPU times increase slightly for all methods. This highlights the trade-off. The fastest methods can be less accurate, while highly accurate methods require more computation. To conclude, this study compared Euler and the mountains and RKF45 for solving higher order ODEs with and without Richardson extrapolation. RKF45 is the most accurate method, closely matching exact solution but more slower. Euler and Adam Mountains is more faster but less accurate. The combinations Richardson extrapolation for with both Euler and Adam Mountains improve significantly in accuracy. For RKF05 combined with the Richardson extrapolation, however, give no additional advantage since RKF05 already controls the error very well. Therefore, if the accuracy is the priority, RKF05 is the best choice. If speed with reasonable accuracy is priority, Euler or Adam Mountains combined with Richardson extrapolations are more practical. That concludes our presentation today. On behalf of my team, I thank you for your kind attention.